Let's take a look at the intermediate value theorem, another theorem that looks kind of obvious once you start thinking about it. We'll also take a look at some other seemingly random problems. Let's say we know that f of 1 is 2 and f of 5 is 10. Is there ever going to be a c where f of c is equal to 2? Well, yeah, I've graphed what we know about this problem so far, that f of 1 is 2 and f of 5 is 10. And that's really all we know are these 2 points on f of x. So do we know that f of c can equal 2? Well, yes, of course it can. We're told f of c equals 2 right here when c equals 1. But how about can f of c equal 4 or 6 or 20? Well, if here's 4, here's 6, and 20 is way up here, can we be certain that f of x is ever going to achieve any of those values? And with what we know, we don't really know much. So the answer to all of these is maybe, don't know. Maybe the graph comes to this point 1, 2 from underneath. And then as soon as it gets into this range between 1 and 5, it goes south. And maybe it's not defined anymore after that. And then we hit f of 5 is 10, and coming out it's just a horizontal line. All right? In this case, f of x is never 4 or 6 or 20. But as soon as we add one more crucial piece of information, we learn a lot more about the function, and that is that f is continuous. As soon as f is continuous, then we know a lot more about it. We know what's happening in between 1 and 5. Not exactly. We don't know exactly what's happening. But we do know that since f is continuous, we have to be able to connect those 2 points somehow. We don't know still don't know what it is coming in to that range. And we don't know what it is coming out of that range. But we do know that in the middle there, we have to hit some of these values. We do know that we have to hit 4. So yes, there would be a c where f of c is equal to 4. And that c would have to be on the interval from 1 to 5. Right? Is there a spot where f of c equals 6? Yeah, there is. And that c would have to be on the interval from 1 to 5. Don't know what's happening outside of this interval from 1 to 5, but we know that in between, definitely going to hit 4, definitely going to hit 6. Are we going to hit 20? Well, the way that I have it drawn, it doesn't look like it. But remember, we don't exactly know what's going on in here. We just know that it's continuous, right? That there's no breaks, there's no gaps or anything like that. Maybe this function all of a sudden dips down way low, goes way high, and then comes out. Right? We're uncertain. So if the graph looked like this, we would find a c where f of c is equal to 20. But we don't know that it looks like that either. All we do know is that we have to be able to connect those 2 points. And at the very least, it would happen in a straight line. And it could wobble off of that in lots of different ways. But we do know that every value in between 2 and 10, all of these values are going to get hit. There is going to be an f of x that takes on every value in between 2 and 10. Outside of that, we're unsure. So is there a spot where f of c equals 20? We would say maybe, but we don't know. So the actual intermediate value theorem, what it says is that if f of x is continuous, and that continuous part is very, very important. If f of x is continuous on the interval from a to b, then there is some c on that interval from a to b such that f of c is in between f of a and f of b. So basically, if you have a point a f of a, and b f of b, everything in between those f of a's and f of b's is going to happen, right? We have to be able to connect those two dots if f is continuous, which seems kind of obvious when you think about it. Moving on to a few more problems that we want to practice here. Let's say that f of x is equal to 1 over x. Find the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. Obviously, our first step is really just to substitute. We haven't taken the limit yet, so we have to keep that limit notation around. But f of x plus delta x is 1 over x plus delta x minus f of x over delta x. Now, we have this complex fraction. So I'm going to keep this limit notation around while I handle this complex fraction. And I don't like having fractions inside of fractions. So what I'm going to do is, instead of dividing by delta x, I'm going to multiply by 1 over delta x. I mean, that's the same as dividing. Then my numerator is here. And it makes the fraction a little less complicated. Next thing, still not taking the limit yet. So I keep the notation around. But I want to simplify this subtraction that's happening in the middle there. So in order to do that, we need common denominators. Inside the parentheses, my common denominators are going to be the product of those denominators. X plus delta x times x. Right? But what happens in my numerator is that this first one gets multiplied by x, and the second one gets multiplied by x plus delta x. And now we need to just simplify all of that. This is where the biggest mistake happens. I'm still just simplifying my expression, so I'm not taking the limit yet. Still need my limit notation around. I'm multiplying by a fraction here that has x plus delta x and x as the denominator. But when we go to simplify that numerator, people go about it too fast. And I see this happening all the time. You go back and say, oh, x minus x leaves me with delta x. And that's not exactly true. If you slow down and actually simplify what we have there, we really have 1 times x is x. And when we distribute that negative 1, we are subtracting x, but we're also subtracting delta x. So yes, those two x's cancel, but we're not left with delta x, we're left with negative delta x. And that delta x will cancel with the one that's in the fraction in front. So when everything is all said and done, what we're left with is a numerator that is negative 1. Right? Everything else is gone, even that minus. So we are looking at the limit as delta x approaches 0. My first fraction is gone. In my second fraction, I have negative 1 over x plus delta x times x. And we're going to let all of the delta x's turn to 0. So that's only this term right here turns to 0. So we can now evaluate the limit. We'll be left with negative 1 in the numerator and x times x, or x squared, in the denominator. Another one of these limit problems, let g of x be the square root of x, and we want to find the limit as x approaches a of g of x minus g of a over x minus a. So of course, first, we're going to just substitute. So g of x is square root of x, and g of a is square root of a over x minus a. And the real kind of trick to this problem is how you view that denominator. And the denominator really is the difference of two squares. So we can factor it. Right? Difference of two squares, like when we have x squared minus 25. We love that one because it factors into x plus 5, x minus 5. And And I'm saying that x minus a is also a difference of 2 squares. So we can factor that one as well into a plus and a minus, which is what are the terms in there. And it has to be the square root of each of those. So we'll have square root of x, square root of a, and then square root of x minus square root of a. In my numerator, that's just the same. And so we get a little canceling to happen. Square root of x minus a, square root of x minus a, both of those cancel. So we're left with just a 1 in the numerator, and then square root of x plus square root of a in the denominator. Now we're ready to take the limit. And what we want to do is take this x and let it approach a. And we'll be left with 1 over square root of a plus square root of a, which of course is 1 over 2 square root of a. All right, let's use a sign chart to help us sketch the graph of y equals negative 2x plus 1 over x minus 2 squared. All right. First, we have to identify our most important numbers, and there are 2 of them, negative 1 and 2. Negative 1 is important because that will make the entire fraction equal 0. 2 is important because it'll make the denominator equal 0, so that's going to be a vertical asymptote. When we go for the sign chart now, all we have to do is test each interval. So if I pick something extraordinarily small, like negative 1 billion, negative 2 is always negative. But negative 1 billion plus 1 is negative. Negative 1 billion minus 2 is negative. But we're going to square it, so that's going to be positive, making the entire fraction positive. As I pass over negative 1, it's x plus 1 that changes sign, so my fraction is now negative. And as we pass over 2, it's the denominator, x minus 2, that changes sign, but we're squaring it so it stays positive, and nothing really in our fraction has changed, so we're still negative. The next thing we want to do is to be able to identify any asymptotes. And the thing about y is that if I were to distribute, we get 2x squared minus 2. And in the denominator, we'll have x squared minus 4x plus 4. And the limit, as x approaches infinity, is going to give us where our asymptote is going to be. Because an asymptote is the line approached by the graph at extreme values of x. So asymptotes have nothing to do with the middle of the function. It's always about the ends of the function. And when we look at this function, negative 2x minus 2 over x squared minus 4x plus 4, it's really only the leading terms that matter. Because as x is extraordinarily large, negative 2x is, much more negative than negative 2 is. And as x gets really large, x squared is much bigger than negative 4x or plus 4. So we only really worry about those leading terms. And so that would simplify to just negative 2 over x. And as x gets very, very large, that limit is going to approach 0, which means we have a horizontal asymptote at y equals 0. All right. Now we've got everything that we need to come up with a good graph. I know that when we're very negative, the graph is going to be positive, and it's going to approach our asymptote. Then it's going to hit 0 at negative 1 and get over to this vertical asymptote. Okay. As we pass over negative 2, the function stays negative, but is close to our vertical asymptote. And as x gets larger and larger, we'll approach that horizontal asymptote. And there's a really good graph. Finally, let's divide 2x squared plus 3x plus 1 by x minus 5. I like the x minus 5. That's a nice linear factor, so we can use synthetic division. And that means bring down the 2, and then multiply by 5, 10. We'll add those two together, 13. Multiply by 5, 65. And add those two together, 66. Which means, when we divide this out, we're left with 2x plus 13 plus our remainder, 66, over x minus 5. And man, that tells us a lot. Like if we're dealing with f of x is equal to this function, and we wanted to graph it, well, we would have to identify our important points, which means we have to factor that numerator first, which it can be factored into 2x plus 1 and x plus 1 over x minus 5. So I see that we have 3 important points. There's one at -1, there's one at -1/2, and an important point over at 5. 5 is important because it makes the denominator 0, so we have an asymptote. The other 2 are important because they make the numerator 0. So those will be x-intercepts. We can go ahead and do the sign chart, testing each interval. So if I pick something extraordinarily negative, 2x plus 1 would be negative, x plus 1 would be negative, and x minus 5 would be negative. As we pass over 1, x plus 1 changes sign, so the entire fraction changes sign. As we pass over -1/2, 2x plus 1 changes sign, so the entire fraction changes sign. And as we pass over x minus 5, that changes sign, and so our entire fraction changes sign. The last thing we need is going to be any asymptote that we have. And if we looked at the limit as x approaches infinity of f of x, we're going to get the limit of 2x plus 13 plus 66 over x minus 5. I mean, we just said that that is what f of x is equal to. And as x approaches infinity, we'll have infinity plus 13. And for the fraction, the denominator is getting very large, so the entire fraction is going to approach 0. Overall, our limit is going to be infinity, which means it's going to grow forever and ever and ever. But more importantly, we can see where our asymptote is right here. We have an oblique asymptote for the line y equals 2x plus 13. I mean, without any regard for scale, we'll have an oblique asymptote like this. And now we're ready to graph. So when x is less than -1, we're going to be negative and approaching our asymptote. Between -1 and -1/2, it's positive, but connecting zeros. And then from -1/2 to 5, it's negative, but coming over to a vertical asymptote. After 5, we are positive, so we have to be above the x-axis. And we're going to have to approach our asymptote. So we can't do this because we have our portion here that is underneath the x-axis, and we need to stay above the x-axis, which means that the other branch has to be up here. And that's a sketch of what f of x would look like.